negative cosine, right? So you say, well, f of x is the sine, right? So big F is going to be negative cosine, right? This is the antiderivative of little f, right? So you know that the integral from 0 to pi of sine
is negative cosine phi minus negative cosine 0.
yes. Right? So negative cosine pi, that's 1, plus negative cosine 0 is 1. So you get 2. Right? Okay. Okay. Okay, any questions? Any questions? Okay. Maybe some other exercises. Suppose I ask you, say, I don't know, this one. Okay. So here's another one. Take 1 minute and do this one. Somebody's asked you the definite integral of e to the minus x between -2 and 9. So you need to find an antiderivative of e to the negative x, and then you need to evaluate it. Okay. Again, turn to somebody nearby and tell them what your answer is or what you did. Okay. Anyone want to tell me? What's the answer? What would you like to say?
I have no idea.
You have no idea. Okay. Can you tell me what function, when you differentiate it, gives you e to the negative x? What function, when you differentiate it? I guess you miss. I don't know your name. What's your name? Luansi. Okay. Yeah, Luansi. What? Can you find an antiderivative of e to the minus x? What if this were e to the x? What's an antiderivative of e to the x?
EX.
E to the x, right? So that'd be nice, but it's not e to the x. It's e to the minus x. So you're looking for something. When you differentiate it, you get e to the minus x. What happens when you differentiate e to the minus x? What do you get? You get minus e to the minus x, right? So it's almost what you want, except that you have this minus sign on it, right? So you don't like the minus sign, so you say, okay, I'm going to multiply everything by -1, right? So you just put a minus sign on this thing, right? And you know that the derivative of -1 times this is going to be -1 times the derivative of the previous guy. So that gives it to you. Okay. Right, so that's this thing, negative e to the negative x is an antiderivative of e to the minus x. Right. Is that clear how we figured it out? We did it just by guessing, basically. You say, well, you know, if I differentiate this, I get negative what I'm looking for. I get negative of what I'm looking for. Well, if I get negative what I'm looking for, I just multiply it by negative, by a minus sign, and then when I differentiate it, I get what I'm looking for. Okay. So that's it, right? That's the hard part, and then all you need to do is evaluate, right? So what's the answer? What's the answer? It would be negative e to the negative 9 minus negative e to the negative 2. Right? So negative e to the negative 9 plus e to the 2. Right? So very close to e squared. Right? This number is tiny. Okay. Let me show you some notation. Usually people write it like this. They'll write negative e to the negative x evaluated between negative 2 and 9. Okay, and what this means is negative e to the negative 9 minus negative e to the negative 2. Okay, this is shorthand for this. This is just an abbreviation for this. Okay. Another example, say secant squared s ds between pi over 3 and pi over 4. Secant squared, right? So does anyone remember the antiderivative of secant squared? Who said it? Yes, Chandran, help. Tangent, yeah. So it's tangent. So you get tangent evaluated between pi over 4 and pi over 3. Right? So a lot of the trouble of doing these problems is just figuring out or remembering the antiderivative. Right? So you get tangent pi over 4 minus tangent pi over 3. Okay. Okay. Any questions on using the fundamental theorem of calculus? This is actually usually called the second fundamental theorem of calculus. Any questions about using the second fundamental theorem of calculus? Okay. It's very helpful, right? You're trying to find the definite integral. All you need to do is evaluate the difference of the of any antiderivative at the endpoints. Okay. This is great. Right? You don't have to worry about anything that happens in the middle. You just find an antiderivative and evaluate at the endpoints and take the difference. Okay. So why is it true? Right? Why is it true? Why does this happen? Why does this great thing happen? I'm not going to tell you right now, so just wait. Before we get to it, we'll do first. We'll do the first fundamental theorem of calculus. Okay. So we just abbreviate this, the fundamental theorem of calculus number 1. Okay. Okay, so the first fundamental theorem of calculus will give us the second fundamental theorem of calculus. So we'll talk about but the second fundamental theorem of calculus is somehow easier for people to understand. And so usually when you're teaching, you start with the second fundamental theorem of calculus, and then you talk about the first fundamental theorem of calculus. Okay, so here it is. The first fundamental theorem of calculus goes like this. Let f be continuous on AB. Okay. Let capital F be the definite integral from a to x of little f. Okay. So this is some sort of area function. Okay, area function based on little f. Okay, so the picture is like this. You have your function little f, okay, and then you make a function big F. So if somebody says, what's big F of x? It's the area, it's this area. Okay, big F of x is the area from a to x under little f. Okay. Area under little f from a to x. Okay, that's what this big F function is. Okay, so for example, what is big F of A? If I ask you, what's big F of A? What's big F of A? Well, it will be the area from A to... It'll be the area from A to A. The area from A to A, which is just 0. It'll be 0, right? Because it'll be, right, the area from A to A. But there is no area. There is no area from A to A. It's just 0, right? 0. Okay. Right? Big F, right? Big F of A is the integral from A to A of little f, right? But that's just 0. Is that clear? If I say what's big F of B, well, that would be the area from A to B. That would be the whole thing, right? Is this clear? Yeah. If I say what's big F of X, it's the area from here to here. Okay, so back to the theorem, right? So you have this function that's continuous. You have a continuous, again, this means continuous. You have a continuous function on AB, and then you have this area function guy. Then, big F is differentiable. On AB. And, in fact, big F prime turns out to be little f. Okay. Big F is an antiderivative of little f. Big F is an antiderivative of little f. Okay, so fundamental theorem of calculus 1 is basically a way of making antiderivatives. Okay, a way of making antiderivatives. A way to make antiderivatives. Right. You have some function, you can make an antiderivative of that function. Okay, this is it. This is it. Right. You have some function, you make a new function, and then it turns out that if you differentiate that new function, then you get back your old function. Okay? So you have some function, you make this new function out of it, the area guy. If you differentiate the area guy, you recover your original function. Okay? So this is like a very brief statement of the fundamental of the theorem. Okay, this basically says the same thing here. Okay, just very concisely. Okay, so if you have some continuous function, you make this area function out of it. Then in fact, the derivative of the area function is the original function. Okay, so you can create an antiderivative for any continuous function. Okay, so let's see, we have 15 minutes left. Okay. Okay, so let's keep on going. Okay, so I was thinking to give you a break, let you get up for a minute, but we don't have time, so let's just keep on going. Okay, so why? Why does this work? Why does this work? Why does this work? That this thing is an antiderivative. Okay. Okay. Well, if we y is f prime big F prime little f. Okay. Well, consider big F prime of x. Okay. So this is maybe this will be the most complicated thing we do today, right here. Okay. So get ready. So f prime x, right? What is that? That's the derivative of big F. Right? Well, we said earlier, what is that? That's going to be the limit of f of x plus h minus f of x over h as h goes to 0. Right? That's what the derivative is. Okay? That's what a derivative is. Okay. So, well, now let's think about this a little bit more carefully. What's f of x? What's big F of x? And now I realize that I have not smiled at all today, so I'm going to try and smile. Okay, enough smiling. Okay, okay, back to it. What's big F of x? You know what it is. There it is right there, right? The integral, it's the definite integral of little f from a to x, right? So let's say the definite integral of little f from a to x. What's big F of x plus h?
A to x plus h.
A to x plus h, right? And we're dividing this whole thing by h. Right? Right. Okay, can somebody tell me something about this? The integral of little f from a to x plus h minus the integral of little f from a to x. What's that?
It's the area of h at plus h.
Yes.
It's
A x plus h, right? You're taking the area from a to x plus h, and you're subtracting off the area from a to x, right? So what are you left with? The area. What are you left with? X to x plus h, exactly. X to x plus h. Right? The area from here to here, right? And then divide that thing by h. Right? Because you took the area from a to x plus h, you took the area from here to here, right? And then you subtracted off the area from here to here, and you're left with this area, right? You're left with this area, the area of under f, the area under f from x to x plus h. Right? Okay. Is that all right? Everyone okay? Any questions? Okay, so now let's think about this thing. You're taking the area from x to x plus h, and you're dividing by h. What does that give you? What does that give you? Where is the h in this picture? Where is h? What's h? Width, actually. So this width here. Yeah. So h is this width, right? Yeah, or length. But I'm not going to call it length. Okay. It's the width, right? So you're taking this area and then you're dividing by the width. What does that give you? That'll give you the length of, it'll give you a height, right?
Yeah.
But what does that height represent?
Average.
The average height, exactly, very good, right? That will be the average height, right? If I have this area here, right? Suppose I have this area, and then and this width is h, right? If I take a over h, what will that give me? That will give me the height of a box where the area is a, right? A over h is the height of a box with the same area as this area, right? So this is the average value of f on x plus h. Right? The average value of f between here and here. Right? Because what we have is this area A, right? We have this area A, and then we divide it by h, and we get the average value, right? The average height in this time. Okay. Okay. So what happens as h goes to 0? Well, as h goes to 0, I'm going to be taking the average value of f in this thing as the interval becomes smaller and smaller. What will happen? It will give me so I should probably say don't say it out. Don't say it out. Let people think. Let people think. But you already said it, so yeah. So you get f of x. Right? You get f of x because you get the average. Each of these things is the average value over this interval, but then you let the interval become infinitely small, right? As that happens, the average values are going to get closer and closer to f of x, right? Right? You have this thing, x plus h, right? Right? you get the average value, but as your h gets smaller, right, as your h gets smaller, the average values are going to get very close to, and in fact they turn into f of x. Right? They turn into f of x, and so you get f of x. Okay. And so, so that's why it's true. The derivative of this area guy is your original function. Okay, so for example, if I say something like this, what is the derivative of the integral from 0 to x of e to the t squared dt? Okay. E to the t squared dt. What is the derivative of this? Okay. This looks kind of scary, but you say, this is just the area guy for e to the x squared. Right? So what's the answer? Go ahead. E to the x squared. E to the x squared. Right? Because this thing here, we just said that if you make a function like this, then it's the antiderivative of the integrand. Right? This is the antiderivative of its integrand, e to the x squared. Right? Okay. Right? If I say, I don't know, say, what is the derivative of the integral from a to x, from 0 to x of the square root of 1 minus t squared dt? What's the answer? Somebody who hasn't spoken too much? Somebody else? What's the answer? How about you, Miss, with the Colorado University?
I have no idea.
You have no idea. Okay. Well, this is the area function. This is one of those area guys. And what we just said is that if you're differentiating an area guy, you get the integrand. Okay? So you just say, well, this looks very hard, professor, but in fact, all you get is the square root of 1 minus x squared. Right? That's what we just said. If you make this area function guy, and you can use whatever dummy variable you like, t or s or whatever. Just don't use x because we're already using x as the boundary. Right? Then, when you differentiate it, you come back to your original function. Okay. So it's in this sense that differentiation and definite integration are inverses of each other. Okay. Right? You create this area function based on the definite integral, and you differentiate it, and you get back the integrand. Okay. Yeah. Is this clear? Is this clear? This is clear. Let me do something a little bit more complicated. It's just a tiny bit more complicated. Suppose I say something like this: the derivative of 0 to the sine x of e to the t squared dt. Okay, so slight complication. Okay. Suppose I give you something like that. So try to take half a minute and see if you can find the answer. Work on it for half a minute, please. Okay, turn to somebody nearby and say, all this is using the blah, 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 blah. Okay. Can somebody tell me what's the one other idea we need to combine here? There's just one other thing we need to bring in here. What is it? What is it? There's just one other theorem that we need to, one other rule or law or property we need to combine. The chain rule, exactly. The chain rule, right? Because this is, right? If we write this area guy, right, then what this is f of sine of x, right? All this is the area guy, but evaluated at sine of x, right? So what do we get? We're going to get f prime evaluated at sine of x times cosine x, right? But what's f prime? F prime, right? F prime x is e to the x squared. It's just e to the x squared, right? And so you get, what do you get? E to the, what do you get? What should I write here? Thank you. Great. Sine squared x, cosine x. Right? That's just a chain rule. It looks complicated, but all it is combining the previous stuff with the chain rule, with the stuff we just did with the stuff from a long time ago. Okay. Okay, that's it for today. That's it for today. So we did not do everything I hoped to do today. I was hoping to do use substitution. So I will send out the homework pretty soon, I think. No? Okay. So for the homework, yeah. So you have a sort of short assignment for tomorrow. Okay, so here's your first assignment. Do 5.4.